Let's continue with lecture 15. This is the second and final part on the chemistry of Americium and Curium for Chemistry 418. The readings for part 2, same as part 1, the chemistry of Americium, and then the chemistry of Curium, those chapters, and the chemistry of the actinides and transactinides. In this lecture, we're going to cover the metallic state of Americium, talk about Americium compounds, Americium solution chemistry, and coordination chemistry. An example of the Americium metallic state is shown here. The metallic state, very much like any other metallic state from at least the initial look. But what we're going to see compared to something like plutonium, it's going to be much, the complexity is going to be lower. The role of the F electrons is diminishing. The number of phases are going to be very different than plutonium, and the melt point is going to be higher than plutonium. Then we'll move on within this part to discuss the nuclear properties, production, metallic state compounds, solution chemistry of curium. And here we have an example of curium. Again, it's glowing. The glow is also an indication of what isotope this curium compound is. The longer-lived isotope, something like curium 248 or 246, would not have this glow, but something short-lived, like the 18-year curium 244, would have this glow. So we know that this is a compound of curium 244 compound. Important compounds of Americium for the nuclear fuel cycle start with the metal and the alloys. Americium metal can be produced by a number of reduction reactions, starting with the fluoride with liquid barium or lithium. The oxide can be formed with the lanthanum species. There's also a number of other reduction routes that are available. Once the metal is formed, there's interesting properties of the metal where 3 phases listed here can be formed with the metal. And this higher temperature phase of the body-centered cubic is within the literature, there's some debate on the exact nature of that species. So even the fundamental properties of Americium, such as the metal, is open to some interpretation in the literature. The metallic properties are relatively non-magnetic, ductile, and there's a lot of interest in understanding the behavior of the metal properties due to the 5f electrons. These 5f electrons tend to delocalize under pressure, and this is also the reason why we get different structures from the hexagonal closed pack to the face-centered cubic and then this body-centered cubic. There's also some discrepancies between experiments and theories related to the formation of these different phases within the Americium. A number of Americium alloys have been prepared. The ones that are important for the fuel cycle, neptunium, plutonium, and uranium, those phase diagrams of the alloys are available. Other important Americium compounds for the nuclear fuel cycle include oxides and hydroxides. 3 oxides have been examined and evaluated: the monoxide, the Am2O3, and the Americium dioxide. There's difficulty in formation of the monoxide because of the instability of the divalent Americium. If one looks at the literature, there's ranges of the lattice parameters, which is always indicative that the compound is not stable and possibly further experiments should be performed. The Am2O3 is the trivalent Americium. It can be prepared under reducing conditions at 600 degrees, and at higher temperature it oxidizes in air. There's phase transitions of this material going from body-centered cubic to monoclinic between around 460 to 650 degrees, and monoclinic to hexagonal between 800 and 900 degrees C. From the phase diagram, one can see where the trivalent Americium oxide species is preferentially formed as a function of the atomic percentage of oxygen. Americium dioxide is preferentially formed, and it can be produced by heating Americium compounds in air or oxygen from 600 to 800 degrees. The main structure is face-centered cubic, and this face-centered cubic can expand due to radiation damage. The formation phase is shown here in the phase diagram of americium with oxygen. Higher oxides can be stabilized through the formation of mixed metal compounds as shown here, since americium does have higher oxidation states. Neptunium hydroxide, which can be formed from the precipitation of americium-3 in basic solutions, is similar and isostructural to neodymium hydroxides. The compound can be crystalline, but becomes amorphous due to radiation damage. The hydrolysis constants and the solubility constants are known, and this behavior between crystalline and amorphous variations is reflected in the KSP. There's a number of organic americium compounds for the nuclear fuel cycle. Oxalates are important, or compounds that can be produced for purification and separation. Here's a list of a number of americium compounds with different organic ligands. Thionyl trifluoroacetone, TTA, is often used in separations. And oxalate is used as a starting compound for the precipitation of americium to the formation of the oxides. One of the important or an interesting consideration for the americium compounds are the resulting colors, and again that's due to the variation of the oxidation states of americium. Americium coordination chemistry is limited compared to some of the earlier actinides we've examined. There's about 50 known coordination compounds, primarily examined through X-ray diffraction. Often what's done is the data is collected and the resulting structure is compared to lanthanide compounds with the idea that americium-3 would be isostructural to trivalent lanthanides. Halides have been examined with relatively large coordination numbers, anywhere from 7 to 11, and often these coordination environments include water. In some species, such as the chloride may be coordinated through an outer sphere with the americium. Structures have been for divalent, for the dihalide, trihalide, and a mixed oxyhalide species have been evaluated. The coordination of americium oxides is shown to be isostructural with plutonium oxides. This isn't too surprising since they have similar ranges of oxidation states. The AM203 has a distorted OH symmetry, and the bond distances for the americium oxygen have been evaluated. The unit cells are shown below for the dioxide, the monoxide, and the AM203. The organometallic chemistry of americium has been examined primarily with the CP ligands. The americium-3 CP compound has been examined and found to be isostructural to plutonium-3 species. Spectroscopy has indicated that this compound is highly ionic, and this information is used for calculations to discuss the 5f and 6d orbital interactions in the CP compound. The ring structure with the cyclooctatetraene ligand, the bis compound is shown here for americium, has been examined. This compound is shown to be isostructural with both plutonium and neptunium compounds. There's differences observed when compared to the plutonium and neptunium compound, particularly with some of the spectroscopy. There's an indication that the 5f electrons in the americium are tuner to form sigma bonds with the organic and do not participate, unlike the lighter actinides. We'll now turn our attention to curium. Curium has a number of isotopes from 237 to 251 as shown here. Important curium isotopes for chemistry include the 242, very short, relatively short-lived, about half a year, high degree of heat per unit mass. The curium 244, which is more widely available, longer half-life, 18 years, activity as far as heat per unit mass is much less than the 242. And then the longer-lived isotope 248, with a half-life of 3 times 10 to the 5th years, is limited in quantity, let's say on the order of 10 to 20 milligrams, and this is often used for target production for the formation of transuranic elements. And here we see routes for the production of the 242 to the 248, which generally involve multiple neutron capture from lighter targets. An example of this successive neutron capture production for curium isotopes is shown here, where plutonium-242 eventually makes its way through capture, beta decay, and capture to curium-244. Further capture on the curium-244 produces isotopes up to the 248. The even isotopes are favored in the production, mainly because of the higher fission cross-section for the odd A isotopes. One can achieve, from this you would see that the curium-248 would have a mixture of isotopes, extremely difficult to separate. However, pure curium-248 can be available from the alpha decay of californium-252. There were large campaigns to produce curium based upon initial kilo levels of plutonium. Curium-244 separations from this plutonium involved dissolution of the target and removal of plutonium by solvent extraction, and then americium curium separations based upon the ion exchange with or solvent extractions with weak amines in high lithium chloride solutions. We discussed this work in the previous americium section. Other separations with americium could include the oxidation of americium to the 5 and the precipitation of the americium 5 carbonate. The aqueous chemistry of americium is dominated by the trivalent state. It has 9 coordination with water, so a very high degree of coordination. And inorganic complexes of curium are very similar to the americium species, with many constants determined by, this is time-resolved laser fluorescence spectroscopy. Curium, like uranium, can undergo fluorescence. Americium also undergoes fluorescence, as we discussed. The lifetime of the americium compound of americium fluorescence is generally measured in nanoseconds. The curium is much larger, and we'll discuss this in a little bit in this lecture. The hydrolysis constants of americium have been evaluated, permitting the speciation diagram of americium, where we see that in most cases, this is an example of americium speciation as a function of sodium chloride concentration, where the americium species is trivalent, is a free metal, generally up to pH 6, and above pH 9 we get the dihydroxide. The primary oxidation state of curium in solution is trivalent. The UV visible spectroscopy is shown here, where there's absorbances between 375 and 400 nanometers. These absorbances are very sharp. The peaks are sharp due to F into F transitions, and again, because of their F to F transitions, not only are these peaks sharp, but the molar absorptivity is relatively low. Curium-4 can be formed, however, it's prepared and stabilized under some extreme conditions. Here's shown the UV visible spectroscopy of curium-4 in 15 molar cesium fluoride. This curium-4 species is really, it's metastable, and this is due to the fact that the curium has a half-filled f orbital. So there's a large oxidation potential of going from the 3 to the 4, and this is also the reason why curium does not exhibit the higher oxidation states as one sees in americium. One of the interesting spectroscopic properties of curium is fluorescence, and a diagram of fluorescence is shown here. This would be the excitation of a curium compound based upon the UV visible spectroscopy. So for curium-3, as we discussed in the previous slide, absorbances between 375 and 400 nanometers would excite the electrons to a level where they will undergo an emissionless relaxation to a state which has 7/2 spin, which is the same as the ground state, and then there was a fluorescence emission. The energy and the lifetime of this process can be measured, and that gives information about the electronic structure. The electronic structure is dictated by the speciation of the curium. So this fluorescence process is very sensitive to evaluating curium speciation in solutions and solids. An example of this curium fluorescence is shown for curium hydroxide species. The absorbance, again, could be in the UV region between 375 and 400 nanometers, with the fluorescence between 595 and 610 nanometers. The energy, both the actual energy of the fluorescence and the lifetime of the fluorescence, is dependent upon the coordination environment. And here we see, in this example, we see that as we change, imagine we're doing a titration on curium, we're adding base, so we're changing the pH, we're increasing the pH from around 6 to close to 10. And one of the things we observe is that as the pH increases, we see a shift from this peak to this peak. Looking at the speciation diagram at around pH 6, this is primarily, this fluorescence behavior is primarily due to the free curium. As we increase pH, we go to the curium monohydroxide and then the curium dihydroxide. The other interesting property that's observed is the concentration of curium in this study. The concentration is at nanomoles per liter. Due to the titration, the concentration of curium decreases throughout this experiment, and we can see a spectroscopic signature from curium from 64 nanomoles per liter all the way down to 3 nanomoles per liter. So this fluorescence technique is a very powerful tool to evaluate the speciation of curium in systems. Curium separations are very similar to what we've already described for americium. So this is just a review. Again, tributyl phosphate can be used, not at the high acid concentrations that are useful for plutonium and uranium, but at lower acid concentrations. HDEHP can be used in nitric and lithium chloride systems. CMPO, curium can be treated similar to what was described for the americium. Ion exchange, again with the lithium chloride, nitric, and HCl systems, where this work exploits the formation of anionic chloride species at the high lithium chloride concentrations. And then precipitations, particularly from americium, can be used by the fact of precipitating out the americium 5 carbonate species. And then any sort of purification based upon precipitation of curium can be done with hydroxide, oxalates, or fluoride, similar to the conditions that were described for trivalent americium. Curium metal can be produced very similar to the route that was described for americium, using the fluoride and barium or lithium, or reduction of the curium dioxide with a magnesium zinc alloy. The melting point of curium metal is higher than the lighter neptunium and americium actinides, and it's similar to gadolinium. There's two structures, hexagonal closed pack and face-centered cubic. That information is shown, the information on the metal phases, melting points, are shown here, and data on curium ions, including the ionization potentials and ionic radii, are listed here. The metal itself is susceptible to corrosion due to self-heating. Formation of oxides on the surface have been identified. This is primarily true with the curium-244, the shorter half-life. And alloys have been examined, the curium-plutonium phase diagram studied, and then curium compounds with noble metals. For instance, if one takes the dioxide and hydrogen, heats it up to about 1500 K in platinum, iridium, or rhodium, you can get a number of intermetallic species with curium. The oxides, there's two primary oxides, the trivalent CM203 and the tetravalent CM02. The CM203 will decompose to the more stable tetravalent oxide at around 600 degrees, and the CM203 does do a phase transformation at around 800 degrees to the monoclinic form. Similar to the americium, the curium dioxide is the stable state and can be made by heating in air or under oxygen. Curium compounds including oxalates or curium on resins, or even the curium trivalent oxide. This compound is shown to have the face-centered cubic structure. The oxides of curium are similar to the oxides of plutonium and some of the lanthanides based on the phase diagram, and some mixed oxides have been examined based upon properties of the isoelectronic lanthanides, where one would expect superconducting properties. However, the curium compounds do not superconduct. Other curium compounds include the curium-3 hydroxide, and this is just precipitation from solution, and it can crystallize by aging in water and has the same structure as the lanthanum trihydroxide. Curium oxalate, it can be prepared from aqueous solutions, and there's stepwise removal of the water under helium, and the system can become anhydrous, removal of all the water, close to 300 degrees. This compound will convert to the curium-3 oxide around 500 degrees, and closer to 600 degrees this will oxidize to the curium dioxide. Curium nitrate can be produced by evaporation of curium and nitric acid. Again, heating this up, you'll get a final product of the dioxide. And there's some evaluation of curium organometallics compounds. Again, the CP ligands, similar to the americium, have been evaluated, and weak covalency, similar to what was seen with the americium, is observed. Unlike the americium, however, strong fluorescence, due to what we described from the curium-3 properties, is used to probe and understand the behavior of this system. An overview of this lecture is presented here. The important information is production and purification of americium and curium isotopes, identifying that there's curium-244, curium-248 are important isotopes for doing chemistry. As for the americium, it's the 241 and 243. Understanding how these isotopes can be produced and how they can be separated should be an outcome of this lecture. Also, some information about the metallic state, the different phases. Fundamentally, the americium and curium metallic states are less complicated compared to the plutonium state. So the role of the F electron seems to be is decreasing, resulting in fewer phase formations. There are minimal range of compounds of both americium and curium produced. There's some limitation on the data, and for the actinides, this represents a very interesting boundary for doing experimental studies. The solution state chemistry of these two elements is primarily dominated by the trivalent state. However, one of the main differences is the americium can form the eel +5 and +6 ions, where curium does not. And the coordination chemistry, again, similar to compounds, is limited primarily to the difficulty and lack of working with these materials and lack of starting compounds. Some questions you should be able to answer based upon these lectures are shown here. What's the longest lived isotope of americium? And as we discussed in the first lecture, americium-243 is the longest lived isotope. And if you want to do chemistry, that's the easier one to use, although americium-241 is easier to get a hold of. Which americium isotope has the highest neutron-induced fission cross-section? Well, we know that we want to look at an even A americium isotope, and if we, by inspection, we see that americium-242M has a cross-section of around 7,000 barns, the largest cross-section for americium isotopes. What three ligands are used in separation of americium? Well, the very similar ligands that are used for other actinide separations, tributyl phosphate, amines, CMPO, HDEHP. What are the solution conditions? These solution conditions can vary, but generally they're acidic aqueous phases with the ligand dissolved in an organic phase. What column methods are useful for separating the americium from the lanthanides? Well, lithium with ion exchange achieves separation from the lanthanides for the americium isotopes. And which compounds of americium can be made by reactions with the elements? Well, the first one is always easy, alloys. Those are just the metals brought together. And then if I react the americium metal, the elemental form, with elemental forms of the halides, I can get americium halides. What sort of americium coordination compounds have been produced? CP ligands, the workhorse for a lot of synthetic organometallic chemistry, have been produced. So trivalent CP compounds. And what are the absorbance spectra for americium and for the different oxidation states? And here we have an example of two. This is americium 5. You see some indicative peaks, particularly here at 514. And then for americium 3, for americium 5. And then for americium 6, we see this peak near 1000. And if we had americium 3, we would see a peak that would be closer to 500. So there's a smaller peak, about 503 for americium 3. Some questions related to curium are shown here. Which curium isotopes are available for chemical studies? Well, curium-244 with a half-life around 18 years is the one that's most available, although one of the nicest to use is curium-248, which has a much longer, thousands of year half-life, although it's much harder to get. Describe the fluorescence process for curium. Well, what we see is that we use an optical route, so basically imagine like a laser tuned to a wavelength where the absorbance occurs, where the electron is excited to a higher energy state. There's a radiation-less relaxation, and then a de-excitation with emission of a photon. A good excitation wavelength is 375 if you look at the optical emission, or excuse me, the optical absorbance spectra for curium. You'll see that 375 is a reasonably good peak. 400 could also work. It also depends upon the strength of the laser system, but one thing you do notice is that the wavelength of the excitation will be less than the wavelength of the emission because of the energy change. What methods can be used to separate curium from americium? Well, we describe some of the column chromatography methods, but also a good method would be the oxidation of americium to the 5 or the 6 state, where curium cannot be oxidized to those states, and then achieve a separation from the oxidized americium from the non-oxidized curium. How many states does curium metal have? What are the melting points? Well, curium metal has 2 states, double hexagonal close pack and face-centered cubic. And its melting point is around 1345 degrees C. So going from plutonium higher in the actinides, we see that we get fewer phases, and also the melting point goes up. What are the binary oxides of curium? Well, you have the trivalent, so CM2O3, and the tetravalent, CMO2, which will form upon heating in normal atmosphere. Well, that would be the dioxide. Right, and you've completed Lecture 15, which you've done now. Provide comments on the blog and respond to the PDF quiz.